Hello. The purpose of the following demonstration is to show Gary, DraftScience, that 2-to-1 ratio masses launched off a lever at 1-to-2 inverse ratio velocities by their respective positions on the lever only have the same momentum, in other words mass times velocity, when launched simultaneously, and neither the lever mass or the operating force have much bearing on the 2-to-1 ratio velocity being achieved. In other words, the 2-to-1 ratio velocity is virtually guaranteed because of their placement on the lever. This contrasts with, now this is the really important bit, the difference between propelling objects off a lever at the same time, maintaining that 2-to-1 relationship, that 2-to-1 ratio, and when you do them separately off the same spring using the same force, you get totally different results. 4 different speeds of balls from 3 different experiments. Yeah, all will become clear. Take your time. It's not worth rushing. This contrasts with when the same masses are independently launched from the same places on the lever, as in the former instance, they will each achieve faster speeds due to the lever force not being shared between them. The half mass will not go twice the speed of the full mass, despite it being in the same place on the lever. In my example, it went 1.69 times faster. Excess lever mass probably accounts for the result not being closer to 1.4, because ideally half the lever could have been cut off while launching the full mass, because the excess length then serves no useful purpose and only slows the lever down as if it was still launching the unused part of the lever at 2 times velocity relative to the full mass. In other words, it's wasting energy moving a long length of lever it doesn't need to be moving. Therefore, the result should have been closer to 1.4, I think. Apart from anything else, this should be useful information to other people who just want to see the movement of levers, launching items, and relative speeds that they go at. It will give you a better insight as to how levers generally work. Thank you for watching.
Okay, so you can see the it's released by that pin there. That pin hooks into there, so it's a sudden release mechanism. Okay, let's do just the green ball first of all. Again. Okay, 4. Now, so just the yellow half ball. Okay, 4 of those. Now both together. This is the only real 2-to-1 situation.
Now this next go, something must have been wrong because the speeds were completely different than the other 3. First 3 that we've just seen, the 2 going together, they were all bob on exactly the same. Then this next one, the green one went much slower and the yellow one went a bit faster, which is unusual. So obviously the green ball mustn't have been touching the lever or something. I don't know yet. I'll have a closer look in a sec. I can just see the lever move a little bit before it touches the green ball, so it mustn't have been in contact with the lever. So that meant that it gave the yellow ball a little bit of extra strength at the expense of the green ball.
Okay, So Gary forgets that we've got this situation, 2 different speeds of the balls, that situation, a different speed of the ball, and that situation, a different speed of the ball.
Now, it's very important to notice that this is the only situation where there really is a genuine 2-to-1 relationship between the balls, because they're being fired off the lever at the same time as each other. So it's inevitable that one goes twice the speed of the other. But that's not the case when you fire them off individually. That's the purpose of this demonstration, to explain to Gary why his conclusions are wrong, because he constantly thinks there's only 2 situations, the half mass going one speed and the full mass going a different speed, where he thinks there's automatically a 2-to-1 relationship, and there isn't. And there isn't. There's only a 2-to-1 relationship where they're being launched by the same lever at the same time. There's only a proper 2-to-1 relationship where they're being launched off the lever at the same time, because then the 2-to-1 relationship is inevitable. It's not inevitable. It's quite impossible, really, when you do it the other way around, launching them individually. That's the point I'm trying to get across to Gary. That's the point I'm trying to get across to all the other people who keep supporting him in his nonsense claims. They need to pay attention. There are 3 situations here, 4 different speeds of balls, 3 different situations, not 2, and 2 speeds of balls, which Gary seems to think there is. There isn't. Wrong, 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 wrong. So we're going to do some frame counting, the most reliable, simple way of measuring the speed of these things. We're going to be counting from when the ball is at that 0 line to when it reaches the 4.5-inch line. The soundtrack will go out of sync with the division, because my computer doesn't like playing back 120 frames per second footage at the same time as me recording of it.
Okay, let's do just the green ball first of all.
That's my pin release lever on the left. A pin locks into the aluminium channel. I do 4 runs of each. See, you just heard it go, didn't you? But you didn't see it go. So the sound is out of sync. Here we go. So I now have to click through. You'll hear me click, 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 click. That's 120 frames per second. There we go. So we're going to count from when the ball, well, I suppose about here really, because it's the next click is going to be over the start line. Green ball. 1. See, it's gone over the line. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I'm taking notes as I go so I can calculate the averages later. 20. So
Okay.
I do 4 of each. You see the lever letting go? Alright, so from here, this time it's bob on the edge of the start line. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. 19 on that occasion. Okay, I'll do an average. I'll take 4 of each and do an average. Let's go number 3 of the green ball. Here we go. Yeah, it's just gone over the line really. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I think 20 is fairer really, because it had gone over the line, hadn't it? So it needs to go over that line. Here we go again. Here we go. From here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, 20. Okay, so that's the green ones done with. Now the yellow ones. Now Gary would argue that the yellow ones, being half mass, twice as far along the lever, will go twice the speed. It's worth repeating that that only happens where they're being launched at the same time off the lever, so that that 2-to-1 relationship is tied in. If they're being launched individually, it's not. All the energy can go to one ball or the other. It's not divided between them.
Now, that's just the yellow half ball.
There we go. Ooh, that's fast, isn't it? The previous one was significantly below the line, and this one is significantly past the line. So I should score a half already, shouldn't I? We'll add a half at the end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11.5, yeah. Here we go. That's on the edge of the start line, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here we go. Okay, I suppose that's bob on the edge of the start line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to say 11 and a half. 11.5. One more of the yellow. Here we go again. Fourth go. Yeah, that's gone over. So we need to add a half at the end because the clip before it was significantly before the line and now it's significantly past the line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 and a half, I suppose, again. Now the next one, we do them together. So I'll be measuring the yellow ball first because that'll be the quickest. From the release point, 1, 2, 3. Okay, they're both pretty much bob on the start line. There's news, damn it, anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'm going to say 13 and a half because it's gone past. 13 and a half for the yellow. Carrying counting for the green. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. 29 for the green. 1, 2, 3. So the yellow ball's gone over the start line, and the black one, the green one rather, is bob on the start. So I'll add a half to the left one, to the yellow one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and a half again. Oh, yeah, 13 and a half for the yellow one. Counting the green one now, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 28. Third go. Okay. Again, I need to add a half to the yellow one, whereas the green one is bob on the start line. So go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and a half. Yeah, 13 and a half again for the yellow. That's a regular thing, isn't it? 13. Carry on counting for the green. 13. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. 27.5 I'll say because that's gone a tiny bit. 27.5. And the last go. This last one had to be scrapped because, well, you might see in a minute when you see the counting, it's obviously wrong. Turns out it's because the ball wasn't quite in touch with the lever when it let go, so it didn't get a proper launch. Like now. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yes, 13. All the others were 13 and a half. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 33. That's an anomaly, isn't it? That's an anomaly, so I think we better discount that one because it's obviously wrong because it's the only one where the yellow ball went faster than 13.5, it went 13. And it's also the only one where the green ball was slower than 20, the 27.5, 28, 29. To jump to 33 is a significant difference. So it mustn't have been in contact with the lever properly or something like that. So I'm going to discount that because it's an anomaly, obviously. Now I'll do the averages of them all. Right, the little bit of mathematics with the calculator, but obviously, my voice went down. Obviously, obviously, I calculated the averages, then did the calculations. But because you watching me calculate the averages is boring, I'm going to cut that bit off and put it at the very end, so it's the wrong way around. So the next thing you'll see is me you'll see me having already worked out the averages and then doing the calculations, what the ratios are. Okay, just trying to make it a little bit less boring. Maths is boring, isn't it? Well, this kind of tedious stuff is anyway. So the greens averaged 19.75 launched on their own. And Gary would say that the yellows, being half mass and twice as far along the lever, should go twice the speed. But in fact, let's see what they actually did go. So I divide 19.75 divided by 11.625. equals, yeah, so 1.698. I call it 1.7. So 1.7. So the yellow ball actually went 1.7 times the speed. Please, please, please don't misunderstand why that didn't come out at 1.4. The reason it didn't come out at 1.4 wasn't because the half mass actually went much faster than it should have gone. No, 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 no. It's that the full mass went slower than it should have gone because it was carrying extra weight. The lever was longer than it needed to be for the half mass. We could have hacksawed off the rest of that lever because it was still propelling a relatively heavy lever. Metal is heavy, even if it's aluminium. It was still propelling that at twice the velocity, as if there was still not quite a half mass, but some mass to propel at twice the speed, and that takes extra energy from the spring. Do you get what I mean? So don't get hung up about thinking, well, that didn't come out at 1.4, that came out more. So the half mass went faster than Steve said it would. No, 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 no. No, it's the other one comparatively, because they were being sent off separately, not at the same time off one. Sorry, I'm struggling to get my point across. The only time that the whole point of this video is to illustrate that the only time you achieve that 2-to-1 relationship is when you send them both off the lever at the same time, so that the 2-to-1 relationship is forced, which is analogous of Gary's so-called lever demonstration, where the 2-to-1 relationship is forced. You cannot alter it. In this situation too, where they've both been forced off the same lever at the same time, the 2-to-1 relationship is forced. You cannot alter it, really, unless other than by minor errors. But the point of this demonstration is to show that when you use the same spring on the same setting, and you individually fire the half mass and you individually fire the full mass at the relevant position on the lever, you get a different result altogether. The relationship stops being 2-to-1. The energy that spring can put into that one mass is going to be exactly the same as it can put into the half mass. The joules are going to come out exactly the same. The input and the output joules are the same, but the results are different. The half mass should be 1.4 if the lever was massless, if the lever wasn't longer than it needed to be for the full mass. Do you get what I mean? I'm sorry I'm getting too agitated. I'm in a bit of a rush. I've got things to do, and it's so much I want to get out at once before I'm busy over the weekend. And I don't want people getting the wrong end of the stick by me rushing. Anyway, well, at least I'm enthusiastic. At least I'm positive. And then the other one, the proper 2-to-1 relationship one, the only one that really is a proper 2-to-1 relationship, is the one where they are fired up the lever at the same time as each other. Then that's the 100% energy input that the spring has got available is split between them. But it's going to be significantly slower than either of the previous examples because of the yellow ball literally going twice the speed of the green ball. It's going to restrict the overall speed of the lever, which is why the lever slows down in these instances where you've got a half mass object 2 times as far along the lever, even though Gary says they balance. They slow down because the lever has to work so much harder to do that balancing. So the average was 28.12 divided by 13.5 average of the others. 2.08. The 0.08 is obviously just the error bar, isn't it? So in other words, it is bob on 2 times the speed here, 2.0. So okay, that works out well. That works out properly. So 2.08 times green. Okay, and that's it then. Job done for that. Stop. Okay, the boring calculations of the averages for anybody who's really interested in seeing every last detail. Now I'll do the averages of them all. Okay, so let's do some calculating. Okay, so let's first of all work out the averages of the first in the greens going independently. So we had 20 plus 20 plus 20 plus 19. Well, that's obviously 79. So 79 divided by 4 equals 19.75. Then we have 11.5 times 3 and a 12. So 3 of those plus 12. So that's 46.5 divided by 4, 11.625 average. Then the greens, we had 29 plus 28 plus 27.5 equals 84.5 divided by 3 because there were only 3 samples that were valid. 28.16. Call it 28.12, I think. 28.12, okay. And the yellow, we had 13.5 times 3, okay. Well, the average is obviously 13.5, isn't it? Yeah, so okay, 13.5, yeah. No need to do that because they were all 13.5. So, right, let's do the calculation then. So, well, you've already seen the calculation now, so thank you for watching.